Okay. While waiting for it to load, good morning, everyone. Good to see a lot of familiar faces here, and thank you for coming. See a lot of people. Very happy to see that we have a lot of interest in this workshop. So in this part of the presentation, I will talk about two things. The first one is impossible differential, and as you all know, impossible differentials over the past 2 years have had a lot of attention. We've had these new models by Hossein Adipur and the people from Graz that do automated key recovery for impossible differentials. We have, I think, a new model by Patrick that will be presented later, and a bunch of other work. And so, like a lot of people last year, we worked a lot on impossible differential within CLASP. And I will tell you a bit about what we did. So in this first notebook, we will see 3 main models. Oh, yeah. Is it okay? One more. Okay. If I can hide the panel and anyway. Okay. So yeah, with that being said, I will start presenting the models, and I know it's 10:05. We have a break at 10:30, and I'm very eager to try that Italian coffee, so I will try not to go over time. And please yell at me if I do. So okay, we will talk about 3 models. One is a word-based model that is inspired by some work that we did with Linkson and some people from NTU a few years ago. Another model for impossible differential is a bit-based model that uses the notion of undisturbed bits, which has been used a lot recently in impossible differentials. And finally, we have a hybrid model that kind of mixes bit-based and word-based approaches, and that was accepted to SAC recently. And I'll be happy to discuss that after the talk as well, if you have more questions. So to start with the beginning, impossible differential cryptanalysis is differential where we look at differentials that have probability 0. So we look for differential propagation that cannot occur. And you're probably already very, very familiar with that. So the first step in doing impossible differential in CLASP is to instantiate a cipher. So here we are looking at 6 rounds of spec. And so as in the previous demos, we first import the spec block cipher, and then we instantiate it for 6 rounds. So then we will build a SAT differential model. So using the models classes that Emma discussed a bit earlier. And yeah, we will instantiate a SAT XOR differential model for spec. So basically a model using SAT that will search for differentials for spec. And then we can fix the input and output values of our differential using these set fixed variables. And then ask the solver to find if there is a differential that satisfies this input and output difference. So that is done by using the find one XOR differential trail with these fixed values where we set the input and output difference. And zoom more. Yeah, okay. Okay. Maybe, do you know if I can remove the left panel actually? I think I tried it already to the max. Yeah. I think somewhere in view. Okay, that is not much better. Okay. Huh. that is the dreaded demo effect. Okay, what is happening now? So yeah, I'm not so familiar with the code server interface yet. One would be command what? Command W. No, that is a bad idea. Okay. Okay, you're back. Okay, so maybe the code will not be that visible, but then we will share the notebooks after the demo, and we can explain how it works, and yeah, we should all be fine. So where was I? Yeah, so basically we set the input and output value, and we try to find a trail. And for this specific input and output differences that we set, there exists a trail, so it's not an impossible differential. And we have the weight of the trail and so on. So we basically found the differential. And then we try with different values with the differential that we know is impossible. And so here we set the input difference to hexadecimal 1000 and the output difference to this. And similarly, we set fixed values and we ask the solver if there exists a trail. And we get that there is no differential that maps this input difference to this output difference, and so the trail is impossible. So that is something that is nice when we know what input and output differences we are looking for, but in the general case, it's obviously not like that. So there are a bit more dedicated approaches to find impossible differentials. And in particular, because if we want to prove that there is no differential, it's not feasible to enumerate all possible inputs and outputs. So one such technique that has been used for a while is a technique where you try all low Hamming weight input and output differences, and you try to find if there is a trail that maps them. So this is what is done here. So you will see the code a bit later, but yeah, basically this method enumerates all input differences with Hamming weight 1, all output differences with Hamming weight 1, runs the solver, and if the solver does not find a trail, then we know it's an impossible differential. So this is implemented in class. It's the basic technique. And here we see that we found 3 impossible differentials with Hamming weight 1. Then there is an equivalent technique for zero correlation linear distinguishers, where instead of trying to find a differential trail, we try to find a linear trail. And similarly, if we find that there are no existing linear trail, we have found a zero correlation linear approximation. Okay, so these approaches work, but they are limited in a sense to very restricted choices of input and output differences and to what you can enumerate efficiently. So the main techniques nowadays use the miss in the middle approach. And there are a few recent works on this, but basically the idea is always similar. It's that you will propagate with probability 1 a differential trail in the forward and backward direction, and you will look for a contradiction. So this is the next approach I'm going to talk about. And for this approach, we have one bit-oriented model, one word-oriented model, and our hybrid model. So in the bit-oriented model, we represent an abstraction of the difference, where we will have a 0 if we have a bit or word that is 0, a 1 if it is 1 or non-zero, and then a 2 if it is unknown. So this model can be used for ARX, obviously, but also for ciphers that have S boxes. And in particular, due to the notion of undisturbed bits through S box transitions, And this notion is very useful for finding truncated differentials. And so the idea is that in some S boxes, you have transitions of this form, where you have, for instance, in the S box of present, if you have input difference 1, then it always goes to an odd output difference with probability 1. So that is why we have this transition here, 0, 0, 1, goes to question mark, question mark, question mark 1. And this is directly visible from the DDT of present. So here we have the differential distribution table. And we see that if we look at the first row, which represents input difference 1, then we see that all the non-zero probabilities are for odd output differences. And so we can directly see that we have this property. Of course, we do it in a bit more systematic way in the tool. But yeah, let's not go through the details. But yeah, so basically we have this model. We propagate probability 1, either 0, 1, or unknown. And then we detect that there is an incompatibility, so a miss in the middle, if on the one side we have a 0, and on the other side we have a 1. So basically, if one trail says that one bit should be 0, and the other trail in the backwards direction contradicts it, then we know that we have an impossible differential. So in CLASP, to use this model, we will first demonstrate it on spec. And here we have a bunch of code that we can skip that is just to have a pretty output, but it's not very relevant to the presentation. And here we also have, if you want to try the notebook later, we also have a piece of code that will check that the impossible differential that you find is indeed an impossible differential. So with that, running the model using the minizing impossible XOR differential, we do find this impossible differential that is displayed here in a pretty-ish format. So we see that on the left, we have the forward direction trail, and on the right, we have the backwards direction trail, and we see that they are incompatible in the middle, or maybe we do not see it. But please believe me, there is one side where there is a 0, there is one side where there is a 1, so it's an impossible differential. And we can verify with that that it is indeed an impossible differential, and yeah, we are all happy. So then we can also enumerate all impossible XOR differential trails. So in this method, we enumerate all the trails, all the impossible differentials that we can find with the model. And finally, the last thing we can do with this model is find impossible differential clusters. And an impossible differential cluster is basically an impossible differential where you allow unknown values in the input and output difference, which can be relevant for attacks, of course. Then, yeah, we have an example on present as well, and it works. Yeah, then we have a word-oriented model, and in a word-oriented model, we have not just 0, 1, and unknown. We have 0, we have non-zero, and we have fixed non-zero. So fixed non-zero means that we know that the value is non-zero, and also it has a value that we fix at some point. And then for the variables that are fixed non-zero, we have another additional set of variables that defines the values. So yeah, and then we have an example constraint. So maybe for this, it's better to look at the paper. I think probably a lot of you are already familiar with it. Yeah, so that is the word-based model, and we look for incompatibilities. And here it's slightly different because we don't have just 0, 1, or unknown, but we have a bunch more variables. But the principle is the same. We look for something that is incompatible in the middle. So here we have an example on L block that, again, I will let you run later. And so we do find this impossible differential. And now I will quickly go over the hybrid model, which is the new thing that we presented, well, that we will present at SAC this year. And for this, I will just go to the picture if it appears. Yes, amazing. Okay. Yeah, so the idea is that if we have a bit-based model, we can lose some information, and that is illustrated on the right, where we have something where we have at some point in the middle, so on this part here on the left of the right figure, where we have something that is 0, 0, 0, 1, that is XORed with something that is unknown, unknown, 1, unknown. And so the result based on the impossible differential models that we are using is unknowns, but actually we lose some information. So we know by construction that the output of the nonlinear function should be non-zero because the input is non-zero. And so this is an information that is lost. And conversely, if we use a word-based model, we lose some other type of information on this propagation. And so in this hybrid model, what we try to do is instead of just saying that it is 0 or non-zero, or unknown, we also have some identifier of the S box that a given value came from. And so this is useful because in the end, we know that all the bits that come out of a S box, if the input was non-null, should altogether have at least one non-zero value. And so that lets us detect some corner cases, which helps in this toy example, and which also was useful for L-block. Okay, so I went a bit fast on this, but I encourage you to have a look at the paper, and I'm happy to discuss the models later. And I think we had a lot of fun with these models, and we tried some new things. So this hybrid model. We also have Simone here that proposed the method to include the technique of hash tables in the key recovery process, which is also in the paper. So overall, that was quite interesting, and I think there are lots of people here that we can talk about it with. I'll be happy to do so after this talk. So now there is 10 minutes before coffee, so I will try not to zoom through and make it unintelligible, but at the same time, maybe skip some parts. So neural cryptanalysis, is there anyone who has never heard of neural cryptanalysis? No? I don't know, I don't trust you, so I will still give a quick overview. So the idea of neural cryptanalysis was introduced by Aaron Gore at Crypto 2019. And the idea is to use machine learning to build differential distinguishers. So we have a schema here. So what happens is that you take pairs of ciphertexts, C0, C1, and you want to know whether they are related or not. So for the pairs that are related, they are the encryption with some key that is secret of a plaintext P0, and this plaintext P0 XORed with a fixed difference delta. So these are the related ciphertexts. And then on the other side, we have the random ciphertext pairs that encrypt unrelated plaintexts. So what was interesting when this paper came out is that it was able to find better distinguishers on 8 rounds of spec than what we would do manually with differential cryptanalysis, and also to improve over the key recovery complexity of the state of the art. And in the paper, in the initial paper, it is compared with a full DDT-based distinguisher where you really build the entire DDT for a given input difference, which takes 34 gigabytes of data. And it performs quite similarly with something that is much, much smaller, super fast to train, and so on. So, of course, in automated cryptanalysis, we are interested in knowing what happens with this. So just to give a quick overview of how it works, but we won't go to the details of the machine learning algorithm. But yeah, it's a neural network that starts with a reshaping of the input. So the input, remember, is a pair of ciphertexts. And because it was proposed for spec, which has 2 branches, then it made sense to divide things into 4 words, 4 16-bit words. as is shown here on the picture. And then there is some special construction, some 1D convolution that lets the neural network learn easily bitwise functions between 4 bits of these words, which basically embeds some information on the structure of the cipher into the neural network, because we know that, for instance, if we XOR the 2 branches, then we get the right branch of the previous round, roughly. And so, yeah, the way the neural network is built helps in learning this kind of stuff. So these distinguishers have some nice properties. One is that they operate in a completely black box setting, so minus this reshaping, but we will go to that later. So they are completely data-based, data-oriented. So that is something that is interesting, and I think the data-oriented approaches are being a bit more popular these days. For instance, with the surrogate differentiation paper by Adi Shamir recently, and it's interesting to see what happens in this black box setting. Then there is the aspect of low data complexity, where these distinguishers typically work with a single pair, whereas in classical differential cryptanalysis, we look for a differential with a high probability. And here we look for different distributions. So in classical differential cryptanalysis, we want essentially something that is flat everywhere and has one peak. We want one differential that has super high probability, and we generally don't care so much about the other differentials. Whereas for neural distinguishers, because they look at one pair at a time, and they have this kind of multiple differential properties that they can look at easily, we are more interested in a different distribution where the size of the reachable differences is smaller, and we have more peaks, not just one. So yeah, this enables low data complexity distinguishers. Yeah, it basically gets multiple differentials and differential linear kind of for free, because these neural networks can look at many different correlations at once. And it simplifies our life in a way, because, for instance, as Juan mentioned in his talk, sometimes for differential linear distinguishers, it's a bit difficult to theoretically estimate the actual bias. And sometimes we have distinguishers that have a much higher bias than we thought, or we have distinguishers where we look at one correlation, but there are multiple masks that have super high correlation. And so neural distinguishers can help identify such things. And there is also the key recovery aspect, which, well, I won't go into detail too much, but here you have an illustration from the paper by Gore, which gives the response of the neural distinguisher, so how its output changes based on the error made in the last key. So when you decrypt the last round with an incorrect key, depending on how far you are from the actual key, you get very different responses, and so that is used in the key recovery. And of course, this is very related to the ARX structure of spec, but yeah, it's something that can be interesting to look at. So in many papers that succeeded Gore's, and in a recent systematization of Lunage paper, we identified over 200 citations. So there are a lot of people that try to build on that. But many approaches use completely different, either different settings, different neural networks, different hyperparameters. There is a lot of fine-tuning involved. And it can be extremely difficult to basically build the best neural distinguisher, or at least a good one. So in an FSC 2024 paper, we looked at how to do that automatically. So instead of specifically building one architecture for one cipher and tuning all the hyperparameters and building a file format and so on, how we can just have something where we click a button and we get some bounds on the neural cryptanalysis for this cipher. So of course, we do not claim at all that this is an optimal way of doing things. We just say that this gives a useful baseline. So basically, if you want to do neural cryptanalysis on a cipher, you can run the AutoND pipeline, and you get the very minimum baseline that you should at least get that. And then, of course, with more dedicated approaches, you will probably get better results. But at the time of the publication of the paper, we we had this table that I will let you through on your own, but where basically we found that with this very generic framework that did not require any interpretation by the cryptographer, we could match pretty much the results of the literature. And again, there are some papers that do better than us with dedicated approaches, and our goal is not at all to have the best distinguishers, but overall we get the same number of rounds, and we get decently accurate bounds with this technique. So in the pipeline, we automate two main techniques. One is the search for an input difference. And it is because, as I was explaining before, we are not looking for one super high probability differential, and we don't care about the rest. We are more looking for a distribution with many high probability things. And so the models that we have at the moment do not work so well for that. So we can try things with truncated differential models. It works reasonably well, but still not so well. So yeah, input difference selection, and then the dataset construction and reshaping. So basically avoiding this thing where you embed the structure of the cipher into the neural network, and the training pipeline. So for the input difference selection, very quickly, the way we do it is that we have some evolutionary algorithm that enumerates a bunch of random input differences, combines them, and so on, and we score them with a scoring function that is based on basically trying to find truncated differentials, because as we identified in a paper with Thomas and people from NTU in 2021, it seems that basically the pairs that the neural network recognizes very well tend to follow a truncated differential, a given truncated differential. And so, yeah, basically what we do here is some kind of frequency test where we look at the distribution of the bits of the output differences, and we try to see some bias in there. And so basically, if we have something that is biased for n rounds, generally we can have a neural distinguisher for n+1, n+2 rounds. And so this is fully automated. So that is something that is quite nice because, yeah, in a lot of papers, the input difference is found a bit haphazardly by taking a good difference from an existing trail, but it does not always lead to the best results. And yeah, so with this empirical approach, we get decent results. So we have a way in CLASP to call this function that finds a good input difference. So here we have an example output. So basically it iterates and it displays the best input differences it found so far, so the most biased ones regularly and with their score and so on. But yeah, the main thing is that it's completely automatic. So you instantiate a cipher, you build a neural network test object for this cipher, and then we'll find good input difference for neural distinguisher, and hopefully it works. So here we see that with running this algorithm on SPEC32, we get the same input difference as the one used in the original paper by Aaron Gore, which is nice, seems to work. And yeah. So then the next point is the architecture and pipeline. And here, without going into details, there are a bunch of choices made by designers of neural distinguishers that have a huge impact on the actual training process, be it the structure of the neural network, the way the input is represented, the hyperparameters. And there was a paper by Gregor and Patrick Neumann on the hyperparameter fine-tuning for neural distinguishers that shows a lot of hyperparameters to tune and a very big impact on a lot of parameters. And so what we wanted to do with this is really, okay, if I have a cipher, I want to know just quick bounds, and I don't want to do all the tuning, don't want to do a deep investigation of architectures and so on. How can I do? And so for that, the short answer is dilated convolutions. And here the idea is that if we want to avoid all this reshaping of the input, if we want to avoid embedding the structure of the cipher into the neural network, using dilated convolutions is a good way. So dilated convolution basically look at spatial information, but with an offset, basically. And so here, what we did is something that combines long-range dependencies, so dilated convolution with high convolution factors, followed by short-range convolutions, so that look at outputs that are close to each other. And this kind of emulates in a generic way all the restructuring that can be done manually. So for instance, for spec, this naturally captures the fact that we have 4 words. It retrieves this information automatically and finds out what to XOR together in quite a nice way. And it's convenient for other ciphers, for instance, for AES, where you will have dependencies within the different bytes, which are interesting to look at, but also within the different colons. And also probably if you're looking at related key, you will have something between the within the rows. So yeah, if you were to do that automatically, you would have a lot of different architectures to test, a lot of different shapes that may work, may not. And yeah, but using the bitnet, you have some result that works, that captures some of these dependencies automatically. And that was the main goal of this approach. So in CLASP, you can instantiate this dbitnet neural network using this function, get neural network dbitnet. You can also instantiate the original ResNet by Gore. And we don't have yet all the other neural networks that were proposed, but yeah, are very, very welcome to add them. It would be super nice to have them in there actually for comparison and for completeness. So, okay, then we basically get a differential data set. So get pairs, some that come from related plaintext, some that come from unrelated plaintext with their labels. And then we train the neural distinguisher, which takes a long time on a CPU, but with a GPU is quite fast. And yeah, that's it. So basically, with these techniques, we retrieve the neural distinguishers by Aaron-Bohr. We retrieve most state-of-the-art results. And it can be run completely automatically in CLASP, just using this run AutoND pipeline. So I showed the steps one by one, just to explain what was going on. But yeah, you can just do the tester.run AutoND pipeline. So the tester is instantiated with a cipher. And yeah, it runs everything automatically. So here we have some output. And then we have the report class that generates this nice report that gives you all the input differences that were found, the accuracies, and so on. Okay, and now maybe something that might be more interesting to some of you. So in the original AutoND repo, we have some custom implementations of primitives that follow a certain format. So we need the input to be a NumPy array of binary value in the format of int, unsigned integer 8 bits, and we have a specific output format. So if you want to implement something in the original repo, it can be a little bit tedious. Similarly, if you want to implement a cipher in CLASP, it can be also a bit difficult with the Sage interface and so on. And maybe you already have an implementation, you just want to test it. And yeah, so in the last 2 minutes of this presentation, I'll just quickly explain how to do that with AutoND. So the first step is to clone the repo from AutoND. And here we have a bunch of shenanigans to just make sure it's in the path and so on. But yeah, the basic idea will be to generate a wrapper for your encryption function. So here we build the encryption function for CLASP, and it needs to have a certain interface. So basically the wrapper that we will provide to AutoND is to take as input a plaintext, a key, and the number of rounds. And it needs to work on binary data as NumPy arrays. So this can be done very simply with a wrapper like that, where basically you encrypt. So yeah, you receive binary data, you convert it to whatever format you want, that is these 2 lines. Then you encrypt it with your implementation, and then you convert it to binary. And yeah, that simple wrapper can be basically copy pasted for any implementation with some small changes and plugged into AutoND. So here we have from AutoND.optimizer import optimize, and here we have this optimizer that finds an optimal difference using our custom implementation. Similarly, for training the neural distinguisher, we have the same thing. So we use our wrapper and we build a data generator that is used in AutoND. And this simple wrapper function does the trick. And we can train our neural distinguisher, and it all works nicely. We get nice results. It's fast, it's good, and everyone is happy, and we get to have coffee. But before that, I'll allow you for 30 more seconds just to tell you a bit about what is next. So we've been working on a few improvements to AutoND that will be on the repo hopefully soon. So we have an improved optimizer that uses GPU-based parallel encryption that lets us test a lot more input differences and also look for biases that are way smaller because we can test a lot more samples that we are doing with people from Milano. We are also looking at prepended differentials, which are used in key recoveries using neural distinguishers, and that we left as a future work in the paper at FSC. And also, a lot of works use feature engineering, where they basically partially decrypt the ciphertext or do other kind of things like that. And so we are working on a technique that implements that automatically with ROPO here. And yeah, and that I think is interesting. And we also have a new approach for key recovery using neural distinguishers that I would have loved to say was accepted at SAC, but was rejected. And so it's not available yet, but I'd be happy to discuss it later as well if you want. So yeah, long story short, if you want to do neural cryptanalysis, please look at AutoND. If you want to do impossible cryptanalysis, you can use CLASP. And just one final word that I forgot to mention, but one advantage of all these techniques is that, for instance, the Aradi block cipher that came out very recently without security analysis, we could just implement it in CLASP, click a few buttons, and get a full security analysis with differential, linear, impossible differentials, neural, and so on. And yeah, quite nice. Okay, thanks a lot for your attention, and I will now leave it to Emma for the final words.
We exceeded a bit the time, but maybe we have a couple of minutes for questions if you want, or if you don't want, we can talk also with the coffee in our hands. Okay. If there is no question, then let's go to the coffee break and let's start again in 20 minutes.